Christine Turner.
I'm Courtney Ammons.
And we did the report on intro to spectrophotometry.
So what we're going to go over is the use of spectrophotometer. So in this just is like the transmittance and the absorbance. We're also going to go over how the lambda.max was found, how we determined the standard curve, and the information gathered by yourself.
The purpose of this experiment was to use the percent transmittance and absorbance found to determine the lambda max of COCl2 from the different wavelengths that is tested at. And once we had the lambda max, we could determine other things, testing different dilutions such as the standard curve, and find the concentration of unknown solutions.
So a spectrophotometer can determine the concentration of a present substance, how the properties interact with the radiation, so just how much light is absorbed by the substance, and then here as well as A equals E times C times L, which is just the quantitative relationship between absorption and concentration.
So spectrophotometry was the method used in this experiment using the spectrophotometer. And this piece of equipment can determine the lambda max based on the highest absorbance, and from this we can make further conclusions.
So what we first did was we had 2 cuvettes. We filled 1/2 of the way with the ionized water, and the other 2/3 of the way with cobalt chloride. The one with water we called the blank, and it was used to calibrate the spectrophotometer. And then we would use the cobalt chloride to read the transmittance and absorbance rates at different wavelengths between 400 and 600 nanometers, increasing by 25. So, and then between each reading, we would recalibrate it with the blank. So, and then we determined that the lambda max was 500 nanometers.
For the second part, 8 COCl2 solutions were made in test tubes, and all of the solutions totaled 5 milliliters with different dilutions of the COCl2. And the spectrophotometer was recalibrated with a blank and set to the lambda max wavelength to test the absorbance and percent transmittance of each of the solutions. They were put into cuvettes and tested in the spectrophotometer, and between each one, it was recalibrated with the blank. And from there, the standard curve was determined.
So we were each given an unknown substance of concentration, and from this we did the exact same steps that she just talked about. We would put the blank in, calibrate our spectrometer, and then we would put in our unknown concentration. From there we get the absorbance and transmittance readings, and we would be able to figure out concentration.
This is table 1, and it just shows the first part of the experiment, the determination of the lambda max. So from this, you can see that at the wavelength of 500 nanometers, we had the lowest transmittance and the highest absorbance, which shows that that's going to be the lambda max.
We had the calculations for nanometers. So it was A equals 2 minus log of percent transmittance. So at 400 nanometers, so we put in our calculations and we ended up with A equals 0.0595.
And this is just a graph showing, it's supposed to be figure 1, I kind of got messed up, showing table 1 of the lambda max. So we can see at the peak there, that's going to be the lambda max at 500 nanometers.
And here we just have the construction of our standard curve. As you can see, we have our test tubes, our volumes of cobalt chloride and deionized water. We would get our transmittance and absorbance at the lambda max, and from there we would figure out our concentration.
This is for test tube 3, showing how we calculated the molarity of the diluted solution. So So we had, the concentrated molarity was 0.150 molar. The volume of this particular one was 2 milliliters, and we know that we wanted to obtain a volume of 5 milliliters total. So using this equation, we figured out that the molarity of test tube 3 should be 0.0600 molar.
And this is our calculation for test tube 3 for E. And we're using Beer's law here, which is A equals E times C times L. However, we're not looking for A, we're looking for E, so therefore we will divide A by C times L. We put in our calculations and we end up with E equaling 5.8 milliliters, liters times mole times centimeters.
It's just showing the standard curve from the 8 solutions we had. As you can see, it's linear and concentration is directly related to absorbance. So the higher the concentration, the higher the absorbance, and vice versa. And we also put in the best fit line, which the equation is shown right there for that line.
So our unknown number was 8 for this one, and our lambda extent is 500 nanometers. And we have our percentage transients and our absorbance, so it was 3.8 and 0.470 for unknown 8.
This is the equation to determine the molarity of unknown 8. We take the equation for the line and we just transfer it to Beer's law. And plugging in the absorbance over here, we have everything else to figure out the concentration. So just solve it algebraically and end up with a concentration of 0.0887 molar.
For unknown number 9, all we did was the exact same steps, just change the transmittance and absorbance, and we ended up with a concentration of 0.101 mil.
So for the discussion's conclusions, we found that percent transmittance and absorbance had an inverse relationship. The higher transmittance was the low, that was when absorbance was the lowest, and vice versa. We figured out that 500 nanometers was the correct value for lambda max, since that was when absorbance was the highest. And also from the standard curve, we can see that absorbance and concentration had a direct relationship, and that the lambda max correlates with the highest absorbance.